Okay, this is lesson 4 of chapter 8, and in this lesson we'll talk about something called resonance, and we'll draw resonance structures. It turns out that some molecules are not well represented by just a single structure, and what the true nature of the molecule is. For example, in this case, you have a single bond on the left side and a double bond on the right. But you could just as easily have written the double bond on the left and the single on the right. So which is it? The truth is it's actually a combination of both. And we're going to draw this drawing both structures and then using an arrow, a double-headed arrow between them to show that the true structure is actually a combination, a blend, or an average of the two. And what we're looking at here is the ozone molecule. Ozone is a famous molecule that this happens in. In fact, if we take a look at the ozone molecule, if we measure the bond lengths, this is customarily done in chemistry, we are able to measure the lengths between the atoms. What we see is that we have equivalent bond lengths. This tells us that the bond here and here is exactly the same. There's no difference. There's not a single and a double bond. And so what we do is we essentially have to draw both molecules following the octet rule, and then we draw a double-headed arrow between them, showing that the true molecule is an average of the two, because that is how nature forms it. So that's how we must represent it. We must represent this molecule as being or having equivalent bonds, and we do this through resonance is the idea. Here's another example of the same thing. So what we have here is HCO2, and in this case you can see that the double bond can be between the right oxygen or between the bottom oxygen, as it is in this case. And it does not matter, both of these connections are equivalent because you have a carbon to an oxygen. Because both connections are equivalent, we have to show them being in both places, and again we show it using this double arrow notation. So we call this the electrons are delocalized. In other words, the electrons are really not sitting between the right oxygen and carbon, and they're really not sitting here either. They're actually in both places at the same time. It's like, if you would, a way to think about it is each one of these bonds is almost like 1.5 bond lengths. This isn't really true, but in truth, this is essentially how it would look. Both these are equivalent, is the idea. A famous case of this actually happens to a molecule called benzene. This will be familiar to those of you that enjoy or are taking organic chemistry. And benzene is essentially a 6-membered ringed molecule. And this ringed molecule has alternating double bonds and single bonds. Double bonds and single bonds. But in truth, all the bonds are actually exactly the same length. They're all equivalent. And the double bond and the single bond idea is really a wrong way of showing it. So what we do is we show resonance again. And very often, especially in the case of this molecule, what we do is there's a way to show all the bonds to be equivalent by drawing a circle on the inside. And again, what we're showing is delocalization of these electrons. They don't really sit in a permanent spot. They move around freely, is the idea. And we can use this idea of resonance to actually predict some interesting ideas or explain some ideas about bonding. So here's a question. Which is predicted to have the shortest sulfur-oxygen bond? SO3, sulfur trioxide, or SO3 2-, the sulfite polyatomic ion. And we'll have to prove this by drawing some Lewis structures. And indeed, in this case, we'll have to draw resonance. So let's go and get to it. So the first molecule, SO3, sulfur trioxide. If we total the number of valence electrons, 6 from sulfur, 6 from every oxygen, there are 3 of these, for a total of 24. So we get 24 electrons. So let's go ahead and draw we'll do one at a time here, and let's go ahead and draw the first molecule here on the left. So, we've got sulfur. Let's try that again. So we have ourselves, we'll go ahead and put sulfur in the middle, because sulfur is the less electronegative element, and we'll go ahead and surround it with our 3 oxygens. So we've got, this gives us 6 electrons. We have to get up to 24. So how about 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That's it. We've exhausted our valence electron count. So what we'll do now is we'll go ahead and put the 2 electrons here to make a double bond, as we've customarily done. So we'll go ahead and get rid of these 2 and put a double bond here. Now the double bond can be in this position, or it can be equivalently in any of these other positions. So we'll actually have to show, because the connection here is equivalent, sulfur and oxygen really on every side, the picture is the same, the double bond can be anywhere, and in fact the double bond is in all 3 positions. So we'll have to draw the other 2 possibilities, showing the double bond on the bottom oxygen, as in this case, and then we can also fill up the rest of the atoms with electrons to ensure that we're showing an octet on every atom. We can also show the double bond being between the left oxygen and sulfur. And again, let's go ahead and put electrons around each atom, ensuring that each has 8. So if you count, every one of these molecules should follow the octet rule, no matter which bonds we're talking about. So in order to represent this as really one molecule, what we do is we draw double-headed arrows between both of these structures. This shows that the real molecule is actually an average of these 3. Now, what we see here essentially in the sulfur trioxide molecule is that we have a double bond divided between 1, 2, 3 bonds. So if you can say that we have a double bond among 3 bonds. So we could say we have 1/3. That's kind of a strange way of saying it, but we have 1 and a third bonds. We can say, you can think of this as having 1 and a third bonds between S and O. So it's not quite a single bond, it's not quite a double bond. Now if we do the exact same thing for our other molecule, the SO3 2-, and for this I'll have to clear the screen, so we'll go ahead and clear the screen, but we'll say we have 1 and a third bonds for SO3. This is from above. Let's go ahead and do the same thing for SO3 2-, the sulfite polyatomic ion. So let's do the same accounting. We have 6 from every sulfur, 6 from every oxygen. There are 3 of these, again for a total of 24, but in this case we have 2 more electrons, giving us a total of 26. And what you'll see in this case, as we draw it, is you'll see that each sulfur, let's go ahead and do the same thing we've done before, so put the 3 oxygens around it, but in this case you'll get 1 structure. You have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and then we're able to put the last 2 electrons around sulfur. So what we have here is we have no resonance, because all of these are single bonds. So we have truly 3 single bonds. So each bond is 1 bond between a sulfur and oxygen on average. We have 1 bond between sulfur and oxygen. So what we have, the question, if you recall, was which has the shorter or the shortest sulfur-oxygen bond. And because we know that triple bonds or double bonds are shorter than single bonds, here we have more, in SO3 we have more double bond character. Double bond character. Therefore, it'll be shorter. So even though we don't really have a true double bond, we have more than a single bond. So the SO3, the sulfur trioxide, will have the shorter sulfur-oxygen bonds. And experimentally, we would actually measure exactly that. Let's also talk about some exceptions to the octet rule. It turns out that molecules don't necessarily have to follow the octet rule. In fact, there are many molecules that do not follow the octet rule. And there are 3 types of these exceptions that we'll talk about. The first type we'll talk about will be molecules with an odd number of electrons. This is strange, but it does occur. Then we'll talk about molecules that have less electrons than 8, and then some that have more electrons than 8. And these, as you'll see, are the more prevalent ones of the exceptions. These would be called expanded octets. So let's go ahead and take a look at these. The first class of exceptions are the odd number of electrons. This is famously exemplified in the molecule NO, nitrogen monoxide. And if you calculate the number of valence electrons that both these bring, nitrogen brings 5, oxygen brings 6, for a total of 11. So there's no way to get an octet around 8 electrons around every atom, because we don't have an even number of electrons. And because nature makes this molecule, we must be able to draw it, we must account for it. And we do this essentially by allowing one of the atoms to have less than an octet. Someone will have 7. In fact, there are two possibilities here. We've drawn the oxygen having 8 on the left side, and then the nitrogen having 8 on the right side. And essentially both of these are possible. Now we have a question here: which of these two is actually the more stable molecule? Remember, we talked about formal charge and how formal charge can allow us to determine which molecule is the correct molecule, and which structure is the correct structure. So let's go ahead and calculate the formal charge on this oxygen, and we'll do so on the nitrogen. Oxygen brings 6 valence electrons from the periodic table, and in this bond we have 1, 2, 3, 4, and then 5, 6. So 6 of these are his. So we'll do 6 minus 6 for a formal charge of 0 on the oxygen. I'll go ahead and circle that. If we do the same thing for the nitrogen here, nitrogen brings 5, minus how many are his? 1, 2, 3, 4, 5, minus 5. And nitrogen also has a formal charge of 0 on the left side. If we do a similar accounting for this nitrogen, we have 5, except in this case we have 1, 2, 3, 4, 5, 6 for a formal charge of 5 minus 6, negative 1. And the formal charge on this oxygen, it actually has 6 minus 1, 2, 3, 4, 5. We have a plus 1 formal charge. So recall that we pick the structure that has the least formal charges, or the more neutral formal charges, as the stable one. So indeed, this is actually the more stable structure. And this is really the way the structure appears. So this is especially true because the oxygen here shows a plus 1 charge, and oxygen is more electronegative than nitrogen, so it should show the minus 1 charge, not the plus 1 charge. So here it is. The second exception are fewer than 8 electrons, and if you take a look, here we have an example where we have BF3, also another real molecule that nature produces, so we have to account for it. Now if you draw the structure of BF3 and then calculate the formal charges, what you'll see is that in all cases fluorine possesses a positive formal charge. Now this is very unlikely for fluorine to do. Fluorine is the most electronegative element, and it will not show itself in these circumstances to show a plus 1 charge, and especially because boron is sitting on the inside and it shows itself to be a minus 1 charge. Boron is quite a bit less electronegative, it's more electropositive. So what we do is we actually allow the electrons to not follow the octet rule, and we do so by essentially putting the boron with 6 electrons. And this is the case. This especially happens with boron. And if we do this, then we'll calculate that the formal charge of every fluorine then is 0, and that of boron is actually also 0. So this follows the octet rule very well. So this is one of those cases in which the less than an octet actually gives us the more important structure, is the idea. And very often this happens with boron. Boron really is the element that that shows this sort of exception the most. So let boron tip you off to that. Anytime you see boron in a molecule, think of less than an octet. And the final exception is when we have more than an octet, more than 8 electrons. So this may sound strange, but indeed atoms can go ahead and bond. It can have more than 8, but atoms from the 3rd period and on And this is so because the second row elements do not have d orbitals. Only beginning with the third row because the third energy level has a 3d subshell containing 3d orbitals where electrons can actually go into. So because of the 3d possibility to use the 3d subshell, then third period elements are able to do this sort of thing. And the extra electrons always go on the central atom. This is important, on the central atom. So we'll go ahead and try this with a few molecules here. How about PCl5 and ICl4 minus? So it'd be a good idea to have a periodic table handy, so that way we could calculate how many valence electrons. So let's go ahead and do this PCl5 and ICl4 minus on the next page. So we got PCl5 and ICl4 minus. So if you take a look, phosphorus has 5 valence electrons. Each chlorine has 7. There are 5 of these for a total of 35 plus 5. We got ourselves 40 valence electrons. In the case of ICl4, iodine has 7. Each chlorine has 7. We got 4 of these. So 7 times 4, 28, plus another 7, that's 35. We have one more here to give us 36 electrons in these cases. Let's go ahead and do the PCl5 one first. Phosphorus goes in the middle because phosphorus is the less electronegative element. And let's go ahead and situate the chlorines around the outside. And you have to fit all 5 chlorines in this case around the outside. And having done so, we could take a look now, get rid of some of this, make ourselves some room. And we got a total of, 2, 4, 6, 8, 10. Keep going until we get to 40 electrons. So 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. So we actually accounted for all the valence electrons, and each element here will show an octet, following the octet rule. So this is how the structure looks. 5 atoms around the central atom. In the case of ICl4 minus, we have iodine in the middle. Iodine is less electronegative. We have 4 chlorines around the outside. Let's do a similar accounting. We have so far 2, 4, 6, 8 electrons. Keep going until we get to 36. So 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Now we've got to 32, but there are 4 more electrons, and the last 4 will actually put on the central atom. So iodine will actually have 2 more pairs, giving iodine a total, if you take a look, of 2, 4, 6, 8, 10, 12 electrons. And this may sound strange, but it is totally fine. Iodine can actually handle 12 electrons. Iodine is actually pretty far down on the periodic table and definitely has d orbitals available, and it's pretty big enough to accommodate a lot of space around it. Iodine is actually a pretty big atom, allowing other atoms like chlorines to bond around it, is the idea. So this would be the structure for ICl4 minus. And that will be the end for lesson 4 of chapter 8.